Hello everyone, welcome to Zoology Made Easy. Today in this video we are going to discuss a little more content about the enzymes and its nature of action. In the previous two, we have already discussed about the active site that is present on the tertiary structure of these enzymes. So whatever the action that is bound up around these enzymes, that is purely because of the active sites that are present on the enzymes. So whenever we are saying active sites on this tertiary structure of enzymes, we shall let us have a recap of one reaction that is taking place here. Enzyme will bind with the substrate and it forms an enzyme substrate complex, which is a irreversible reaction. And this enzyme substrate complex will then get converted into enzyme product complex in the journey of the product formation, and later on the enzyme and the product will get separated. And this enzyme, we have already told about it, this will not participate in any chemical reaction. As it is not participate in any chemical reaction, the enzyme will come out as it is. So this is how it is taking place. But sometimes what happens is this entire process will be inhibited in certain cases, and such a condition we can refer to as the feedback inhibition. It is the feedback inhibition where the enzyme that is formed as a result of the formation of end product. That means the enzyme that is responsible for the formation of this end product, or the enzyme that is coming out along with the end product, that will lead to the inhibition of the enzyme activity. Let us take an example. Here there is an initial substrate present upon which the enzyme should act upon, and this initial substrate will be acted upon by, let us say it is enzyme 1 for instance. And later on, as a result of this action of enzyme 1, certain intermediate compound is formed, and let us name this intermediate compound as A, intermediate compound A. And on this intermediate A, again enzyme 2 will act upon, and intermediate compound 3 will, B will be formed. Intermediate compound B will be formed. Upon this, enzyme 3 will act upon, and it leads to the formation of end product. So once the end product is formed, what happens? This end product will inhibit the action of this enzyme 1. So this inhibition is called as feedback inhibition. That means a sort of signal will be sent to these enzyme receptors where the end product is already formed and there is no further necessity of any secretion of these enzymes. So such an inhibition is called as the feedback inhibition. Now let us see what are the different factors that are affecting the enzyme activity. Very important topic. Good number of questions can be expected from this. The factors affecting enzyme activity. So there are certain factors which either increase or decrease the optimum activity of these enzymes. For instance, let me tell you, there are certain types of enzymes which undergoes a process called as autocatalysis. Sorry, autolysis. Autolysis mean what here? These are the enzymes which they trigger the maturation or they trigger the formation of their own active products. This autolysis or autocatalysis can be observed in certain enzymes such as trypsin. Example is trypsin. Trypsin is itself an enzyme, but this can activate other enzymes, other enzymes, or I can say this trypsin itself can activate its precursor form called as the trypsinogen. Trypsinogen is the form precursor form, whereas the trypsin is the matured form or the active form of the enzyme. So let us see what are the different factors that are affecting the activity of enzymes. The first one is the temperature. In the previous video, I already told you the the temperature forms a very major role in the enzyme activity. Any slight changes in the temperature will either increase in case of increased temperature or will reduce in case of decreased temperature of the enzyme. Right. So these enzymes function under a very narrow range of temperatures. Very narrow range of temperatures. So if at all this enzyme is showing its maximum activity at a particular temperature, maximum activity, let me say, for example, at 30 degrees centigrade, if a particular enzyme is showing its maximum activity, this 30 degrees centigrade will be called as the optimum temperature. It will be called as the optimum temperature. So how do you define this optimum temperature now? The temperature at which an enzyme shows its maximum activity. It is called as the optimum temperature. Let us write that the temperature at which an enzyme shows its maximum activity or its maximum functionality is called as the optimum temperature. Then what happens if the temperature is decreased or increased? If at all the temperature is increased after the optimum temperature, enzyme activity reduces. Enzyme activity reduces. Then you can question me. Previously, you told enzyme activity will be doubled for every 10 degrees rise in temperature. Yes, but till it is obtaining the optimum temperature only. Beyond the optimum temperature, if the temperature is increased, the enzyme activity will reduce. And if at all you are decreasing below the optimum temperature, again the enzyme activity reduces or declines. So both above and below the optimum temperature, the enzyme functionality will be very much limited. But there is one importance in decreasing the temperature. Whenever the temperature is exposed to very low, when the enzymes are exposed to very low temperatures, here the enzyme will become temporarily inactive. Enzyme will be temporarily inactive. And again, whenever you are raising this temperature, the enzyme will become active. This is one of the importance of preserving the enzymes at low temperatures. Whereas, you can ask me, if at all it is low temperature, okay, fine, it is becoming inactive, and when you're raising the temperatures, again, it is becoming active. That's benefit actually. Then what about increased temperatures? Increased temperatures do not exhibit any such benefits of enzymes. It simply leads to the denaturation of enzymes. It leads to the denaturation of enzymes. That means they lose their viability of optimum activity. What is happening then? If at all you are raising the temperature at these high temperatures, what is happening here? The kinetic activity of these molecules, the kinetic activity of molecules becomes very much strong enough to break the weak hydrogen bonds, to break the weak hydrogen bonds. So, where are these hydrogen bonds present? These are present within the tertiary structure of the enzyme. They are present within the tertiary structure of the enzyme. So, whenever this tertiary structure of the enzyme is bonded by these hydrogen bonds are usually weaker bonds. These weaker bonds will be broken by the kinetic activity of the molecules as they have become very much stronger due to rise in temperature. So if at all we plot a graph representing the temperature and enzyme activity on x and y axis, we can get a graph of this kind. On x-axis, we are representing the temperature, and on y-axis, we represent the enzyme activity. So in the initial stages, what happens as the temperature is rising, the enzyme activity also reduces. And once it is reaching the optimum temperature, the optimum enzyme activity in the temperature, it starts declining, it starts getting denatured, right? So we can say this is the optimum activity of the enzyme, the optimum activity of the enzyme. The other factor that is necessary in enzyme activity is the pH. The second factor is the pH, which can be otherwise called as the hydrogen ion concentration. It can also be otherwise called as the hydrogen ion concentration. It, it is a very quite simple thing to remember about pH. Anything that is above the 7 is the basic, below 7 is the acidic, and at 7 is the neutral solution. We all know this, right? Next, we'll see every enzyme, how this pH is related to enzyme. When we are speaking about enzyme here, there will be an optimum pH which is different for each and every enzyme. Let us say in case of salivary amylase, which can be called as the ptyalin, the pH here is 6.8. That means very slightly acidic. Is slightly acidic. But when it comes to pepsin, the proteolytic enzyme in the stomach, the pH is reduced to 1.5 to 2.5. This means it is highly acidic. Again, when you go to pancreatic juices or intestinal juices, the pH will range between 7.8 to 8.2, which is again basic. That means the activity of the enzymes within the different parts of the body would also be dependent on the pH. Just like the temperature, any sort of increase or decrease in the pH will reduces the enzyme activity. It reduces the enzyme activity. So you can say taking these three into consideration. Three examples. Some will act best in slightly acidic medium, some will act best in highly acidic medium, and some act best in the basic medium. And just like the temperature, if we are plotting a graph between the pH and enzyme activity, we obtain a graph of this kind. X-axis we are taking pH, and on y-axis it is the enzyme activity again. So there is also an optimum pH for the enzyme activity to be optimum. So any sort of raise or decrease in the pH also will reduce its functionality. And the third factor that is necessary for optimum functioning of enzyme is called as the concentrate or concentration of the substrate. It is called as the third factor is the concentration of substrate. That means how much substrate is present, whether the concentration of substrate is very much low or very much high. It is also one of the factors which decides the functionality. So increase in the, if at all you are increasing the substrate concentration, we can say increase in substrate concentration, increase in substrate concentration will automatically increase the velocity of enzyme action. Increase in the velocity of enzyme action. That means the speed of the enzymatic reaction will be increased. Uh, this increase in the reaction rate will be up to certain extent, which is called as the maximum velocity, and this maximum velocity will be represented by V max. It is represented by V max. V max stands for what? The maximum velocity. And this maximum velocity can never be increased. It can never be increased, whatever may be the further concentration of the substrate. You have, for example, the Vmax is reached at 10 micrograms of the substrate. Once after Vmax is reached, even if you are adding 10 more micrograms of the substrate, then the Vmax will not be increased. Why? What is the reason for this? Is at this stage of the maximum velocity, the enzyme molecules are fully saturated. Enzyme molecules are fully saturated or completely saturated at Vmax. There are no further molecules that are left over at the active site, or no active site is left free enough to bind some more substrate molecules. Okay, fine, you are adding 10 more micrograms of substrate, but where is the enzyme? Enzyme is not available. So what happens? There will be no further increase in this Vmax. And if we plot a graph for this, on x-axis we consider a constant which is called as the Michaelis-Menten constant. On x-axis it is the substrate concentration, substrate, and on y-axis we are representing the velocity of reaction. We are representing the velocity of reaction, and this is indicated by V. So what happens as the substrate concentration increases, there will be one point where the enzyme reaction will reach a point which is called as the Vmax. So we can say that this is the Vmax, and half of this will be Vmax by 2, and this Vmax by 2 is taken as the Michaelis-Menten constant. Now, there is one constant which is called as the Michaelis constant. Michaelis-Menten's constant, or simply Michaelis constant, and this is indicated by Km. What does this indicate? It indicates the substrate concentration at which the chemical reaction at which the chemical reaction catalyzed by an enzyme catalyzed by an enzyme attains half its maximum velocity, attains half of its maximum velocity. You can see here, wherever you are representing the Km in the graph, where is it plotting? It is plotting at the Vmax by 2. Vmax by 2 is the half of maximum velocity, or Vmax. So how do you define this Michaelis-Menten's constant? We can define it as the substrate concentration at which the chemical reaction catalyzed by an enzyme attains half of its maximum velocity. And there are certain other types of enzymes called as allosteric enzymes, and those allosteric enzymes will never exhibit Michaelis-Menten's constant. Allosteric enzymes do not show Michaelis-Menten's constant. So this is all about the nature of activity of enzyme, the feedback inhibition, and the factors affecting the enzyme activity, where there are three factors. The first one being the temperature, the second one being the pH, and the third being the concentration of substrate. So from this, one question can be asked in the form of graphs, either the temperature graph, pH graph, or the Michaelis-Menten's constant graph. One question is mandatory from these three topics in your NEET. Thank you all. In the next video, we shall see the lock and key theory of enzyme action and the types of enzymes.